Hi guys, very quick update. So today we are launching our blog app. So from today onwards, whatever video I'm posting, all those things will be in a blog format as well. You can get the code there, you can read the entire blog. If you don't have time to see the entire video, you can read up on the blog. So you won't miss anything from video and blog. So everything will be same. So it will be very detailed as well. So you can head over to codewithmagesh.tech, codewithmagesh.tech. You can go to this website and you can see the blog. So far there are two blogs. One is for today video, one is for yesterday video. So I will show you some demo. So this is for yesterday video and you can see this is very detailed, as well as the video will be embedded here. You can see video here also, or you can see in my channel as well. It will start from the problem statement and then I will explain what is the problem. You can see. So before jumping into the problem, let's understand a problem in simple terms. So it will be from a beginning to the end. All those things will be there, even dry run as well. You can see I have written like what actually depth means. Depth is nothing but a longest path from top to the bottom of a tree. I think these things I have said in my video, as well as I have written over there for a better understanding. And you can see I have walked through the example as well, given example. I'm showing which is the longest path and all those things. And then the approach, like DFS approach, I explain each and every step very detailedly. The dry run also here, you can see dry run. Entire dry run is there, and code as well, and BFS solution. This is a BFS solution. And yeah guys, that's it. And if you really like it, please support us, subscribe to the channel. Now let's continue back to the video. Hi everyone, today we're going to talk about a very classical tree problem, which is same tree. What the problem asks us to do is they will give two trees, a two binary tree, and we need to tell whether both are identical or not. That's a problem asks us to do. And what this problem different from other problem in the same category is, a tree is a non-linear data structure. And if you look at arrays list, they are linear one, which means data will be in a linear manner. You can simply loop over both of them and you can tell whether the two given array or two given linked lists equal or not. But we cannot do the same thing over a tree. So in this problem, we'll figure out how to do this efficiently. So let's get into the problem. Now let's talk about what does same tree means. So once we have better knowledge about this thing, we can solve this problem very easily, because this is the main thing or a core logic to solve this particular problem. Now let's understand what is a same tree means. So when do we call a tree same means? If both the trees are empty. If both the trees are empty, they are same. Which means both have null. At this particular point, we can tell it is same. And next, when we can tell both the trees are same is if it satisfies this condition. If both the trees are non-empty, which means some value should at least exist, and that node should be have the same value. This is the valid node. These nodes exist and we have to check the values. The first step is we have to check the values. If both the values are same, then what do we have to do next? Next step is we need to check the left subtree. Next step, let's assume 2 is there, 2 is there. Next step is we need to check the left subtree. And then what is the next step? We need to check the right subtree. So if this condition pass, we can tell that this is the same tree or an identical tree. This is the process which is going to be repeated. It's recursive in nature, because trees are non-linear one, right? It could have a different branches. Let's say this is the whole tree, and we could have a different branch, and this could have a different branch, this could have different branch. So this is a recursive nature. So unlike linear data structure, we cannot determine this is the limit, this is the limit. So we need to do recursively, and we need to check whether it's identical or not with this valid condition. And we can look at some example as well. So let's look at this first example. Just apply the same concept as I said. Apply these things and tell me whether these are equal. What is the first condition? First condition tells that if both the trees are non-empty. Does it non-empty? No, it doesn't. So now let's come back to this particular cases. Now the first case telling us to check the values. Both the values are equal. Yeah, it does. Now what is the next step? Next step is check the left subtree. So now we are moving to this subtree. Now we have to do this process again because it's recursive nature. Now we'll do this process, all this process again for this particular node. We'll do this again. Okay, got it? Note this point. This is recursive nature. So for every particular node, we'll try all these cases. If it pass, then it's identical. So now let's apply all these things. So does this node is empty? No, it doesn't. So we'll move back to this particular cases. Now check both the roots are same. Yeah, it does. It's same. Now what is the next step? We have to check a left subtree. If you look at, there is no left, right? There is no left, which means it is the leaf node and it satisfies this particular condition. If both the trees are same, it's identical. So return true back. I mean, we'll return a true back to this particular parent node, and this parent node will return true to its parent node. And now what is the next step? So we just found seen all the left tree, and we have to look for the right subtree, right? Now let's go for right subtree. So right is 3, this is also 3, it equals, again the process going to be coming from the start for this particular node. So this is also true, it will return back the true to the parent node. So we can conclude that both the trees are identical in nature. If you look at this particular example, first condition pass, which is root value same, but if you look at the left value, here there is a true and here there is an empty node. So which means these trees are not identical in nature, so it is not a valid tree. So we can simply return false over there, and here also same, it's not a valid tree. The roots are same, but if you look at the nodes value, it is completely different in nature. So this is also not an identical tree. We can simply return false over there. Now let's have this idea in our mind, and we'll apply all these valid cases, and we will also derive the base cases as well from this one, and we can solve this problem, guys. Now let's get into the DFS solution. So before moving to the DFS solution, as always I mentioned, we need to find the base cases, right? Now let's figure out what could be the base cases. So we have seen that if the trees are empty, we can simply tell it is a valid tree. So this could be the one base case I'm writing over here. If P, let's assume there's a P and Q tree. If P is equal to null and Q is equal to null. So this is going to be a first base case, which is if both the trees are empty, we can simply return true. That's it. We got one base case. Now let's think about what are the other base cases. So we have seen that if both the values are equal, then we'll proceed the process. Now think hypothetically, what if both the values are different? We can simply tell it is a false case, right? So right, this is also one more base case. If P dot val is not equal to Q dot val, simply return false. That's it. You have found one more base case. Again, if you think with the problem statement, you could derive one more base case as well, which is if either one of the node is empty, we can tell it is dissimilar, right? You can see this particular example. If either one of the node is empty, we can simply tell it is a false. So this is also one more base case. That's it, guys. We already came to the answer. So it's very simple, right? If P is equal to null or Q is equal to null. If either one is equal, it's simply not a valid node. We can return a false over there. And that's it. We almost got all our base cases. Now we have to focus on the recurrence relation, right? What is a recurrence relation? So recurrence relation is very simple. So we can simply return function. So I'm going to call this as a DFS. Now what I need to do, if you remember the valid condition, once we check the root values are equal, next step is we need to check the left subtree. So now let's do that. So we have to do for both the trees simultaneously. Remember, at simultaneously we have to do it. So what we do is P dot left as well as Q dot left. Now what is the next case? Next case is like this should be 100. So and next is what we have to do. We have to check the right subtree as well. So let's apply the same concept for the right. So DFS of P dot right comma Q dot right. That's it, guys. We almost written the entire source code or a pseudocode. Now let's walk through a quick dry run and we can code this up in lead code and we can close this video. Now let me do a quick dry run, guys, so that you can have a better understanding about this particular problem. Again, this is recursive nature, so please pay attention. Again, this won't be a very difficult one. It's pretty easy. So now let's get into the dry run. And initially we are going to have the root node into the call stack. And what is the motive of DFS? I mean, what is the principle? So we'll go to the deep down to the left, and we'll go to the right, and we'll proceed to the root right. So now let's do this process. First, we'll have the root node, and we'll check all these cases over these two nodes. Does it pass? Yeah, both the values are non-empty, so it passed this case. Again, we'll check if the both values are non-equal. No, it's equal, so it also passed this case. And is either one of is empty? No, both is a valid node, so it passed all the test cases. Now we come to this particular line, which is the recursion stack. Now we have to check for its left node. So let's do this. So it will be like 2 comma 2. Again, this will come over here. So now let me move this down. Okay, now we are going to do this process again. So 2 is non-empty. Yeah. And both the values are equal. Yeah, it does. Is either one is non-empty? Nope. So both are a valid node. Now again we'll come to this particular case. So we'll do again the left subtree. Okay, let me do this. So it will be 4 comma 4, or I will also write the recursion relation over there. So at the first we'll do this and we'll pick this one, and we'll start to do this process. I mean this process. Now T of 2 comma 2. What is T of 2 comma 2 relation? T of 2 comma 2 relation is nothing but T of this 4 left subtree, and what is this value? 4. And T of what is the right value? Right value 6. Here also right value 6. You can see right value 6, right value 6. Just put like this. And what is the next step right now? We have to do all this process. Yeah, it passed all these cases. Again we'll come to this particular case. So again we need to go for a left subtree. I mean, this is a basic principle of DFS. Again we'll go to this particular node, which is T of 4 comma 4. Now we came to T of 4 comma 4. So does it have any particular node? I mean, both the nodes are null. Now this condition pass. Okay, you can simply do this like this. T of null comma null again, and T of null comma null. I mean, both the left and right nodes are empty, right? For both the tree, you can see there is no node here. There's no node over here. So again, this call stack will go. I mean, we'll put null comma null. Okay, for better understanding, null comma null. This will go again. Now we'll have this particular case passed over there. So both the nodes are null. So we can simply return true, right? We can simply return true. So this call stack will return true, guys. Let's put true. And now once this done, we'll go for the right subtree. Right now we just came back to the root node, which is over here. I mean, which is over here 4. Now we will go for the right node. Again, the right is also empty, so this will also return true over here. Now what is true? And of 1 comma 1, which is 2 comma 2. Again, obviously it's going to be true over there. Entire thing is going to become true. Now this will return back to this parent. What is the parent of this? True. So this will return true. Now again we'll proceed this process for right subtree, right? Now let's do that. So this value is true, and now we have to proceed for 6 comma 6, right? Now we will remove from the call stack, and I will rub this out. Now we are working on the right part of a tree, which is 6 comma 6. So do the same process again. I will erase this also. I'll do this for same. So T of 6 comma 6. So again, both the left and rights are null. So obviously it's going to be a valid node. So you can simply return true over there. True. What is true and true? It's going to be true. So this entire thing will become a true and will return back to its parent node, which is 1. So this is also true, and we can remove this from a call stack. Just remove this. Now we conclude that both the left trees are equal. Now what's the next step? We need to check for the right tree. So let's apply the same logic here. What's the right? It's 3 comma 3, and we'll do this process again. So T of 3 comma 3 is going to check for its left subtree and right subtree. So what's the left subtree? Left subtree is 5, and T of 5 comma 5. and there is no right subtree, right? So I can directly tell it as a true and true. I mean, there is no right values for this as well as this. So I'm going to directly write as a true value. Now we have to compete for this particular node, right? Again, there's a call stack, which is for 5, 5 in a recursion call stack. So we'll compete for this. So I can directly tell that 5 is a leaf node. So it's obviously going to be valid. So there is 5 is equal, both the 5s are equal. So I can simply tell this value is true and the entire value becomes true. Simple. Now we just return back the value to the parent. So after returning, it will be true. So what is true and true? The entire result becomes true, which means that both the left as well as the right is same, which concluding that both the trees are identical in nature. I hope you understand this dry run. Now let's quickly code this up. Now let's write the base case, guys. So what is the first base case? First base case is nothing but if both the trees are empty, we can tell it as a valid node. If not of P and not of Q, and I can simply tell that it is a true node. It is a true or identical node. Now what is the next subtree? Now what is the next base case? Next base case is if either one of the node is empty, I can tell it as a not valid node. So if not of P or not of Q, I can simply return false over there. Now we have covered two base cases. Now what is the next base case? Next base case is checking the value. If P dot val is not equal to Q dot val, I can simply return false over there. I think I can combine this both in a same if case, but that's fine. Let's have better understanding. Now what is the recurrence relation? So return of self dot the function name, which is same tree, and I'm going to call simultaneously for both the left as well as the right. So P dot left comma Q dot left and P dot right as well as Q dot right. That's it. This is the entire code. Now let me run this. Yeah, it passes the test case. Now let's submit this and see. Hope it passes. Yeah, it does. So I hope you guys understand this particular problem. I explained very detailedly. I don't see about the length of the video. And yeah, thank you so much. We'll see you in one more video. Until then, bye.